Hello, welcome to another problem session. We are going to today discuss a relatively important concept of effective potential energy. You already, I gather, you know what potential energy is. Let me get a thicker pen. You know what potential energy is. I want to talk to you about effective potential energy. So, in gravity, we're going to use gravity as an example. It can be in any other system. You can have electrostatics. Also goes very similarly. Let's look at gravity, and this is Newton's gravity. So, looking at two-body system. So this is Sun and this is Earth, or any two-body system. So this one I'm going to call it M1 and M2, and so you have a kinetic energy of this, kinetic energy of this, and then there's a potential energy, right? So if you were to write the energy for this, you will get half M1 V1 square plus half M2 V2 square plus potential energy, and potential energy will be minus G M1 M2, or a distance separating them is R, distance R. So this is potential energy, and this is kinetic energy. We learned that this system can be actually studied a little bit differently. So we look at the center of mass. Say you have a center of mass here, and if we look at here, potential energy only depends on separation of the two. So we can actually separate out the motion. So kinetic energy of Cm plus kinetic energy about Cm plus this guy. So you can separate kinetic energy into these kinds, and this would be when you work it out, you'll find that this will be simply half total mass M1 plus M2 and V of Cm square. So if I use a coordinate system in which I move with the Cm, and it turns out this dynamics also shows that dvCm vector dt is 0. So this will, if I go in a center mass space frame, it will still remain inertial frame. It still remain inertial. So if I go in this frame, then this whole thing kind of separates out a little bit differently. So we call this, say, R1, R2, I mean, and from here to here, let's call it R1 vector, and from this end to that end is the distance vector, this R, which is R2 R2 minus R1. Maybe I would have done probably M2 as M1, and this is opposite of what we have done before, but let's stay with this right now. For us, M1 is the, if you're in a planet, it's going to be M1 with the sun, and M2 with the planet. So this is in that direction towards the planet, towards the smaller mass. So this thing actually becomes a new problem. The center of mass in this problem, this will be 0 in this frame, and this problem can be shown to be turn out to be half mu v square v of mu. So there's a new particle mu instead of m1 m2 minus g m1 m2 over r. This still stays the same, only changes over here because we just stripped out the center of mass energy, and we go from so this vector here, we move it out here and we place instead of m1 or m2 mu. So if you want to look over here, it's over here, so that's where mu is placed. And so this is our vector, and because angular momentum L is conserved, so this is a plane perpendicular to L. It's perpendicular to L. Okay, so this is at some instant t, the mu is this, and just studying the mu becomes the main thing, right? So this is x, and this is y, and this is theta, and this is r. So this is a polar coordinate now. Now let's look at a little bit more closely this as the energy. Okay, so when I look at the energy just of this two system in this frame is half mu v square minus g m1 m2 over r. So you can see this is the kinetic energy, and this is the potential energy. So this is the potential energy, and this is the kinetic energy. Right. Now in the polar coordinate, we have two coordinates r and theta. They're the functions of time, locating where the mu will be, right? So let's write down in polar coordinates. So this is polar coordinates. So what will it become? This will be half mu dr dt square. So v square will be this plus r d theta dt square. So v square will be this, and the potential energy will be same m1 m2 over r as before. Now because L is conserved, we should be able to write this in terms of L. Okay, so let me erase a little bit and get me some space. Okay, so how to deal with this? How to deal with this term? Okay, so to deal with that term, we think L is angular momentum in this mu times r times velocity perpendicular to it, that's the r. So mu r d theta over dt. Okay, so this is multiplying gives me the mu, gives the L angular momentum magnitude. Of course the direction is perpendicular to it. So this is mu r square d theta dt. We want r d theta dt, so L over mu r becomes r d theta dt. So now just put a number here. That gives us half mu dr dt square, and this whole thing will become plus half L square over mu times r square, and then this guy is g m1 m2 over r. So if you look at this whole thing, the angular velocity is already taken into account here. So this is kind of like a one-dimensional problem. So this is problem of system of mass mu, coordinate and coordinate r, but r is going from r can be between 0 to infinity, only can be positive. This coordinate is just positive, unlike x coordinate, etc. So we can think of this thing as some kind of potential energy, and this thing as kinetic energy associated with this coordinate. So we think of this kinetic energy. So this is kinetic energy you might call it effective kinetic energy, right? Kinetic energy associated with coordinate r. So it's related to velocity of the coordinate r. If the particle is moving away from the center, then it's positive. It's coming towards the center, is negative. And this part is not potential energy, because this is the potential energy. So this whole part, this is the part we call it effective potential energy. One thing to notice is this kinetic energy part, this effective kinetic energy part, this is going to be always, this has to be greater than or equal to 0. Must be, is positive, because this is positive and this is positive. But this can be positive or negative. Okay. I'm going to draw some pictures of this effective potential energy, and you'll see why this becomes very useful. Okay, so this is the effective potential energy. U effective, and you might say this is the kinetic energy effective, although it's just called kinetic energy often. Okay, so energy still is made up of a kinetic term and a potential term. Now let's look at this potential term, so this will have a unit of energy, and it can be positive or negative. So this is a 0. So it's made of two different terms. One is positive, this part is positive, and this with a negative sign is negative. So this part is, let's use a different colors. So this is going slowly as 1 over r, but this is the g m1 m2 over r, and this other part is pretty rapidly going up, and this is L square over 2 mu r square. And when you add them up, you can see that it goes like that, something like that. So this is together, so U effective. You can see that based on where the energy is, in relation to these, with the requirement, this should be positive. So this has to be always greater than 0. Must be. So let's look at can I have this energy at this level? Let me get a different pen. I think so. Can the energy be this? If energy is this level, and so this term is that level, say look at over here. So actually this would be, I mean, take any value, maybe it's better take it over here. So that's the effective potential energy, and this is the energy. Then let's look at this kinetic energy effective. This term is equal to E minus U effective. So this minus that, this is negative. So this will be key effective is negative, which is not allowed. Not allowed. So energy can't be over here. Actually, the lowest energy can be is the lowest of effective potential energy. So that's one case. You might take a case one is energy is equal to the U effective, the minimum that effective will be, and at that point the value, this is the value of R. Value of R is only one value of allowed, and you can see that's a circular motion. So let's call that circular motion. So this is R circular motion. This is one we have been calling R0. Actually, when we solved this problem before, we had a solution of R of t was R0 over 1 minus epsilon cosine theta, and this was actually what the R0 was. Epsilon is 0 for that case. So epsilon is actually square root of 1 minus E over U effective minimum. That's what it turned out to be. So this epsilon is 0. Okay, so let me do that case one. So as I increase, so these E not allowed below this. You can't have a system whose energy is below the 50% energy. Let's look at a next. If I go up in energy, we come across this energy level. Let's call, say, case 2, this value of energy. Now R value can go from a minimum to a maximum. So if this was a solar system, you will call it a perihelion and aphelion. So this is going to go back and forth between these R values. So that just so this is case one was a circular motion, and case 2 will be elliptical motion. Then we come to a point where let's take another color, say maybe lighter color. Let's take this color. So this is energy 0. Energy 0 at this point, this becomes equal to the energy, which means kinetic energy in the R coordinate is 0 at that point. So at that point, dr dt equal to 0, since K effective is 0 at that point. So if you had a particle going coming towards R equal to 0 is where the sun will be, right? A particle coming towards the sun, it will seem to come here and want to go back. And so this will be the change in R, but it's not necessarily coming in a straight line to the sun. It's coming at a in the plane. So the plane will be like this. and where the sun is, and the particle will seem to be coming in and going like that. So it will be minimum distance. There's a minimum distance that it will remain. It will come to, and that will be that point. So that's the minimum distance, but it's not forming a bound orbit like this. There's no maximum distance. So this orbit is unbound, and it's actually, this is this orbit is, if you work it out, it's a parabolic in shape. So parabolic orbit. That's not the only unbound orbit. If I keep going in energy, I'm going to say come across this energy. If energy is that, of course, these you can't come inside here because kinetic energy will become negative. So these are, of course, not allowed for that guy either. Just like for this motion, this range is not allowed. For this motion, there's only one place is allowed. None of this is allowed, and none of this is allowed. So this one, R values are not allowed. Only this value is allowed. You can see that this one does not have bound orbit, right? So this unbound, it can go on forever, and without violating kinetic energy constraint. Okay, so. But the closest can come is over here. So this is the closest approach. So the shape is kind of like this, but not the same. And its shape for this is actually elliptical. For parabolic shape, epsilon equals to 1. By elliptical, epsilon is greater than 1. So this should be plus, yeah, plus, yeah. Otherwise, it's going to be a problem, yeah. Okay. So this is the concept behind effective potential energy. I think that's all I have to say today regarding effective potential energy. What we're going to do next, that there are many systems where the potential energy looks like this, and we are interested in studying motions around the bottom part of it. And next series of lectures I'm going to start is when you have something like this or anything I'm interested in bottom, you can actually replace this to a high degree with a some kind. If this was some function of x, this can be like half kx squared. You can replace that with half kx squared type of potential energy. So if you have some potential energy which is complicated, but you're not interested in way out there, you're just interested in what happens around here. So as long as you stay in very small thing around here, you can study, you can replace the original potential energy by something like that. And you'll see that that kind of potential energy leads to what is called harmonic motion. And we're going to study harmonic motion, in particular harmonic called simple harmonic motion. So we are going to study simple harmonic motion next time onward. Okay, so it's already a long video. Or talk to you later. Bye.